I want to talk about RC circuits now, and then we'll come back to another worksheet on capacitors in series and parallel. RC circuit, that means a resistor and a capacitor. So the idea here we've got a switch, a capacitor, a resistor, and our source of EMF, our delta V, our battery, or a power supply. So that capacitor, there's a reason we draw it this way, right? It's open. It's not a closed circuit. There's a insulator, an electrical insulator in between those plates. Current cannot pass from one plate to the other through the capacitor. But there's some time involved. The capacitor doesn't charge instantaneously. We close the switch, and when we close the switch, charges start to move around. So what really happens, an electron moves counterclockwise, or you could think of a positive charge moving clockwise. But because this capacitor is a reservoir of charge, it can store a lot of charge, we can start to move charges around in this circuit. So we can build up a positive charge over here and a negative over there, right? We can move an electron around. We can move another electron around. And another one, and another one. And as the first one is going to move very quickly. There's nothing preventing it from moving, right? Just a little resistance in the wire. The second one, not only does it have to fight the resistance here, but there's already an electron over there, so we have to fight that, pushing the second one in. So that's a little harder. The third one, it's even harder to push in there. We're fighting two electrons that are already there, right? So you can see how, as time goes on, the flow of charges is going to get slower and slower until eventually it reaches zero, and we say the capacitor is fully charged. So the flow of charges, we call that current, right? If we looked at the current plotted in time, it starts out at some maximum value the instant we close the switch. I'm assuming that capacitor does not have any charge separated, doesn't have any charge stored in it when we, it's been shorted out. There's no stored charge on it. Q equals 0 for that capacitor. Times 0, we close the switch. Charges start to flow. So we get a big initial current in this circuit. And then as the capacitor builds up charge, the current slows down, and eventually it goes to 0. Right? At time equals infinity, it goes to 0. We could also think of it as charge on the capacitor. What would it look like if we had looked at the charge on the capacitor as a function of time? Well, at t equals 0, there's no charge on that capacitor. The instant we close the switch, and then what happens, it starts to build up quickly at first, but then it plateaus out when it reaches its maximum charge, or as it tries to reach its maximum charge, and it looks something like this, where this would be Q maximum. And what is Q maximum? C times delta V. You see that? Because as the current goes to 0, the voltage drop across the resistor goes to 0. Right? Out here, the current has basically gone to 0. So if there's no current flowing anymore, the entire one side of the capacitor is basically hooked up to the low end of the battery, The other side of the capacitor is hooked up to the high end of the battery. So you have the whole battery across the capacitor. Q equals CV for a capacitor. So you can figure out that's the maximum charge you're going to get on that capacitor. Okay, I've drawn these curves. I kind of know something about how the curves are shaped, so I drew them this way. But how do we figure that out? Well, you use the loop rule. You go around the circuit. You say, I go up by delta V. I go down by the delta V on the capacitor and on the resistor, and I get back to the bottom of the battery. And the capacitor, the voltage on the capacitor is the charge over the capacitance. So we substitute that in for delta V on the capacitor. Delta V on the resistor is IR. We substitute that in, right, to that equation. So now we've got an equation that has Q and it has an I. Well, what is I? I is the rate of change of Q, right? Q over time, right? How Q is changing in time. We would write that dq dt, right, as a differential. And this is a differential equation. And when you solve the differential equation, you get this. You get that the current for a capacitor that's charging like this, you get the current, I'm going to do charge. Charge on the capacitor at any time t is given by the maximum value, which I just wrote over here already, is C delta V. All right. Times 1 minus e to the minus t over RC. Let's just make sure this is right. When t equals 0, you get e to the 0 is 1. 1 minus 1 is 0. So we get 0 charge at t equals 0. And when t equals infinity, you get e to the negative infinity. So 1 over e to the infinity, that's 0. This goes to 0. You just get Q maximum. Q is equal to Q maximum as t goes to infinity. And that's what we get when we're charging a capacitor. So it's a good idea to just check your conditions. T equals 0, t equals infinity. Make sure it makes sense. Because it's easy to get the equations mixed up. Make sure you have the right equation. So this is for a capacitor that's charging. You close the switch at t equals 0. It had no charge on it, and it charges up as time goes on. And this tells you, if I knew what R and C are, and I asked you, I told you R is a certain resistance, C is a certain capacitance, and I want to know how much charge is stored on this capacitor 3 milliseconds after I close the switch. We can figure that out, right? And this value RC, we often write as tau, the time constant. So you'll often see this written as T over tau, the time constant, because we want to be able to compare. If I have a circuit, an RC circuit, that has a certain response, and you have one that has a different response, we want to be able to compare them. Maybe this is my RC circuit, and this is your RC circuit. And we want to be able to compare these two. Well, yours charged, if these time axes are the same, yours charged much quicker. By the time yours reached pretty much its maximum charge, mine was about, halfway to its maximum charge. Mine is going much slower. So we want to be able to compare these. Well, technically, they never reach their maximum charge, right? It takes an infinite amount of time. So we need some value that we can compare. So, like I think I mentioned the other day in lab, a halfway value would make sense, right? We could say, well, how long does it take for your circuit to get to half of its maximum charge? How long does it take mine? Right? That would make sense. That would be an easy number to compare. The problem is the math doesn't work out very nicely to get halfway. This would be a weird number here. So we look at the equation, and we say when t is equal to r times c, this works out very nicely, e to the minus 1. So let's use that. Instead of saying the halfway point, let's say 1 minus e to the minus 1 times our maximum value. Let's use that to judge how quickly our circuit is responding. So when the charge gets up to 1 minus 1 over e of its maximum value, we record the time, and then I'll do the same thing on mine, and we call that tau, so we can compare our circuits. So if this would be 1 minus 1 over e of q max, and the time would be tau, which is equal to r times c. And you do the same thing on yours. Q max, 1 minus 1 over e times Q max would be here. And you record the time. And that's when t is equal to tau RC. And then we can compare. Okay, so the time constant of the circuit tells us how long it takes to charge to 1 minus 1 over e of its maximum value. So we have a comparison point.